So in these Nmap lectures, we have seen no port scan, also known as ping scan, different ways of scanning ports, syn scan, also known as half-open scanning, TCP scan, also known as TCP Connect scan, UDP scan, service and version detection, operating system detection, and Nmap scripting engine in detail. Now let's see how we can cope with network security devices such as firewalls or packet filtering. You with me? You'll always face some security measures in your penetration tests. They will got you, drop your packets, or reply some fake responses. So you have to find those measures and bypass them to go on. Network obstruction such as firewalls can make mapping a network exceedingly difficult. It will not get any easier, as stifling casual reconnaissance is often a key goal of implementing the devices. Nevertheless, Nmap offers many features to help understand these complex networks and to verify that the filters are working as intended. It even supports mechanisms for bypassing poorly implemented defenses. One of the best methods of understanding your network security posture is to try to defeat it. In addition to restricting network activity, companies are increasingly monitoring traffic with intrusion detection systems, or IDS. All of the major IDSs ship with rules designed to detect Nmap scans because scans are sometimes a precursor to attacks. Many of these products have recently morphed into intrusion prevention systems, IPSIVS, that actively block traffic deemed malicious. Unfortunately for network administrators and IDS vendors, reliably detecting bad intentions by analyzing packet data is a tough problem. Attackers with patience, skill, and the help of certain Nmap options can usually pass by IDSs undetected. Meanwhile, administrators must cope with large numbers of false positive results where innocent activity is misdiagnosed and alerted on or blocked. So there's no magic bullet for detecting and bypassing firewalls and IDS systems. It takes skill and experience. So here I'm going to show you a few methods to bypass or detect the IDS and IPS devices. Although timing techniques are used to improve scan times, they're also very good at being invisible against the network security devices such as firewalls or IDS and IPSs. We'll see the timing techniques in detail, but let's see the other techniques to bypass security measures. The F option causes the requested scan to use tiny fragmented IP packets. The idea here is to split up the TCP header over several packets to make it harder for packet filters, intrusion detection systems, and other annoyances to detect what you are doing. Specify this option once, and Nmap splits the packets into 8 bytes or less after the IP header. So a 20-byte TCP header would be split into 3 packets. So be careful with this. Some programs have trouble handling these tiny packets. Fragmentation is only supported for Nmap's raw packet features, which includes TCP and UDP port scans and OS detection. Features such as version detection and the Nmap scripting engine generally don't support fragmentation because they rely on your host's TCP stack to communicate with target services. Using well-known ports as the source port of the packets that we'll send is another technique to bypass firewalls. To trust traffic based only on the source port number is one surprisingly common misconfiguration. It's easy to understand how this comes about. An administrator will set up a shiny new firewall only to be flooded with complaints from ungrateful users whose application stopped working. In particular, DNS may be broken because the UDP DNS replies from external servers can no longer enter the network. Here, Nmap offers the source port option to exploit this weakness. Simply provide a port number and Nmap will send packets from that port where possible. Randomize hosts tells Nmap to shuffle each group of hosts before it scans them. This can make the scans less obvious to various network monitoring systems, especially when you combine it with slow timing options. You can use the uppercase S to spoof the scan to make the targets think that someone else is scanning them. Note that you won't usually receive reply packets back. They will be addressed to the IP you are spoofing, so Nmap won't produce useful reports. You can also use some techniques to understand the existence of the security measures. The first technique is to analyze the TTL, the time to live values of the incoming packets. The TTL values of the packets coming from the destination systems may differ from the TTL values of the packets coming from a network security device. So find incoming packets which result two different results and analyze their TTL values. Bad sum option asks Nmap to use an invalid TCP or UDP checksum for packets sent to target hosts. Since virtually all host IP stacks properly drop these packets, any responses received are likely coming from a firewall or IDS that didn't bother to verify the checksum. Correct timing in Nmap scans is important for the accuracy and effectiveness of the scan. In the case of outside scans, it is usually preferable to use slow scans to avoid devices such as IPS and IDS, whereas in a scan from an internal network, quick scan options will be preferred. While the fine-grained timing controls are powerful and effective, fortunately, Nmap offers a simple approach with 6 timing templates. You can specify them with the uppercase T option, and their number, 0 through 5, or their name. The template names are Paranoid, 0, Sneaky, 1, Polite, 2, Normal, 3, Aggressive, 4, and Insane, 5. The first 2 are for IDS evasion. Polite mode slows down the scan to use less bandwidth and target machine resources. Normal mode is the default, and so T3 does nothing. Aggressive mode speeds scans up by making the assumption that you are on a reasonably fast and reliable network. Finally, insane mode assumes that you're on an extraordinarily fast network, or you're willing to sacrifice some accuracy for speed. Max retries option is to specify the maximum number of port scan probe retransmissions. When Nmap receives no response to a port scan probe, it could mean that the port is filtered, or maybe the probe or response was simply lost on the network. It's also possible that the target host has rate limiting enabled that temporarily blocked the response, so Nmap tries again by retransmitting the initial probe. If Nmap detects poor network reliability, it may try many more times before giving up on a port. Now, while this benefits accuracy, it also lengthens scan times. So when performance is critical, scans may be sped up by limiting the number of retransmissions allowed. You can even specify max retries 0 to prevent any retransmissions, though that's only recommended for situations such as informal surveys, where occasional missed ports and hosts are acceptable. The default, with no uppercase T template, is to allow 10 retransmissions. Host timeout is used to give up slow targets. Some hosts simply take a long time to scan. This may be due to poorly performing or unreliable networking hardware or software, packet rate limiting, or restricted firewall. The slowest few percent of the scanned hosts can eat up a majority of the scan time. Sometimes it's best to cut your losses and skip to those hosts initially. Specify host timeout with a maximum amount of time you are willing to wait. For example, specify 30 minutes to ensure that Nmap doesn't waste more than half an hour on a single host. Note that Nmap may be scanning other hosts at the same time during that half an hour, so it's not a complete loss. Nmap utilizes parallelism and many advanced algorithms to accelerate the scans. Especially in the case of external scans, it may be necessary to close the parallel scan. That is, to send a single packet to a server at the same time. Nmap utilizes different options for this purpose. As we saw just a few minutes ago, you can manage the timing using uppercase T option. If you use the templates, 0 paranoid, 1 sneaky, or 2 polite, parallelization is closed. That means these templates serializes the scan so only one port is scanned at a time. Scan delay option causes Nmap to wait at least the given amount of time between each probe it sends to a given host. This is particularly useful in the case of rate limiting. Solaris machines, among many others, will usually respond to UDP scan probe packets with only one ICMP message per second. Any more than that sent by Nmap will be wasteful. A scan delay of 1 second will keep Nmap at that slow rate. Nmap tries to detect rate limiting and adjust the scan delay accordingly, but it doesn't hurt to specify it explicitly if you already know what rate works best. Okay, so by default, Nmap calculates an ever-changing ideal parallelism based on network performance. The max parallelism option is sometimes set to 1 to prevent Nmap from sending more than one probe at a time to hosts. Nmap has the ability to port scan or version scan multiple hosts in parallel. Nmap does this by dividing the target IP space into groups and then scanning one group at a time. When a maximum group size is specified with max host group, Nmap will never exceed that size. So if you specify maximum number of hosts in a group as 1 using max host group option, there will be only one host in the group and only one host will be scanned at a time. So what do you reckon the difference is between the max parallelism and the max host group? Did you see it? When you set max parallelism to 1, Nmap sends only one packet to a host at a time. When you set max host group to 1, Nmap scans only one host at a time.